Welcome to the last part of my lecture on symbiosis. I want to give you one last example of how complex these symbiotic relationships can be in nature. And this example involves leaf-cutting ants that are found in the New World tropics. They're part of a larger group of ants called fungus-growing ants because they actually grow fungus for a food. And in leaf-cutting ants, the workers leave the nest. They go in search of leaves, usually of a particular kind of leaf, depending upon the season. And they cut the leaves up into small fragments and then carry them back to the nest along these long foraging trails that can extend more than 100 meters into the forest. And they can be foraging at several trees at once, and different trails can converge into large freeways. And eventually they carry the leaf fragments back to the nest, and they carry them into the nest where they process them into smaller and smaller pieces. And then they use the leaf fragments to grow a fungus that is their only food. So here's the process in a drawing. The leaf carrier brings the large leaf fragment back, then smaller workers cut it up into smaller fragments and still smaller fragments, and eventually embed the leaf fragments into the fungus, and the fungus then uses those leaf fragments to grow. And then the ants actually feed on the fungus, and it's the only food that the ants eat. And the fungus is also an obligate symbiont of the ants because the only place that we find this kind of fungus is in the gardens of these leaf cutting ants. So on the one hand, the fungus is an obligate mutualist of the ants, and on the other hand, the ants are an obligate mutualist of the fungus, and neither the ant nor the fungus can survive in the absence of the other. So here's what a fungus garden looks like in the ant colony, and it turns out that if you look closely, you'll find another type of fungus that's also growing in the fungus garden, and this fungus is a parasite of the cultivated fungus. It's in a different group of fungi from the cultivated fungus, and it is every bit as specialized as the cultivated fungus. These Escabopsis parasites are only found in the gardens of fungus-growing ants, and different species of fungus-growing ants, which have different species of cultivars, have different species of parasitic fungus. So in this case, we have another symbiosis in which the parasitic fungus is a parasite on the cultivated fungus, and it also has a negative impact on the ant because the ant can't survive without its cultivated fungus. So it turns out that there is a fourth participant in this network of symbiotic interactions, and that is a species of bacteria that grows on the body of the ants. And the ants actually cultivate that bacteria. They have special places on the body where the bacteria grows, and the ants actually feed the bacteria and cause the bacteria to grow. Now, this bacteria produces an antibiotic that's toxic to the parasitic fungus, and the ants both passively and actively apply this antibiotic to the parasitic fungus, and that kills the parasitic fungus. The ants also obsessively prune the fungus garden, and they can identify the parasitic fungus from the cultivar, and they can remove it physically as well. Now, it turns out that this is a very old interaction, about 50 million years old. And if we look at the phylogeny of the ants here, and the phylogeny of the cultivar, we see that the phylogenies match up pretty closely. And that's because the fungus, the cultivated fungus, is actually transmitted vertically or maternally, if you will, from one colony to the next, because when the founding queen leaves to start a new colony, it takes a little bit of the fungus from her natal colony to start her new colony. And it also turns out that if we look at the phylogeny of the parasites, they also match up pretty closely with the phylogenies of the cultivar and the phylogenies of the ant. So this suggests that there's a lot of very close coevolutionary interactions that have been occurring between all three of these participants. And if we look at the phylogeny of this bacteria, we find, or the phylogeny of the ants and the bacteria, we find that, again, the different ants have different structures on their bodies that they use to cultivate this bacteria. And again, these specialized structures provide a house, a home for the bacteria, and also food for the bacteria. And in return, for a place to live, the bacteria provide the ants with this antibiotic, which they use against the parasitic fungus. So again, this is a nice mutualistic interaction between a bacteria and ants. So we don't know how common these complex symbiotic networks are in nature, but I suspect they're a lot more common than we think. And I'd like to leave you with 3 questions regarding the kind of interaction that I just described, but it could apply to other networks of interactions as well. And first, the relationship between leaf-cutting ants and the abiotic-producing bacteria have lasted for 40 million years. So why hasn't antibiotically resistant forms of the parasitic fungi evolved? Because this is something that we deal with all the time. When we develop an antibiotic, often it doesn't take very long for the target to evolve immunity towards that. So how has this antibiotic been effective for so long? What are the ants doing, or what are the fungi doing to prevent this kind of antibiotic resistance? And secondly, leaf-cutting ants are a dominant herbivore in the neotropic forests and grasslands. They are a major pest in domestic crops in the areas where they occur. And how do they select the vegetation to harvest? And do they take into account what the fungi needs to pick the kinds of leaves or other vegetation that they will harvest and bring back to the nest? And how would we figure that out? That suggests that the ants and the cultivar are communicating with one another in some way. And again, finally, it's nice to wonder about how common these kinds of complex symbiotic relationships are in nature and why we don't know more about them. Okay, so here's your study guide. Here's a list of 5 things that you should be able to do based on this lecture, and that's all I have to say.